Hello, I'm Rishang, and today I'll be presenting our work on relational abstractions for generalized reinforcement learning on symbolic problems. Deep reinforcement learning has been shown to be successful in image-based tasks like Atari games. However, many problems do not have natural image-based representation. As a motivating example, consider a system administrator problem consisting of n arbitrarily connected computers which can be off or on, and the agent is a system administrator who can either reboot a specific computer or do nothing at any given time step. Computers can stochastically turn off with a failure rate which is proportional to the connectivity properties of the network. The agent is awarded with a reward proportional to the total number of computers that are running, and the action dynamics are unavailable, making reinforcement learning the natural choice to solve such problems. Now, this problem cannot be easily expressed as an image-based representation, but is easily expressed using first-order logic predicates like running and linked to indicate if a computer C is running or if two different computers are connected or not. In fact, many such problems, real-world problems, already have factored representations written for them and are readily available, making relational representations in RL an attractive avenue for solving. One key problem with relational representations in RL is that it's not tractable because the state spaces grow exponentially as the total number of state variables increase, making techniques like Q-learning not computationally tractable. One solution is to compute generalized policies, which are policies that transfer to a class of problems for a domain. For example, given the system administrator example, a generalized policy could be to reboot any computer that is not running, else do nothing. This generalized policy usually yields much higher rewards compared to a random policy. It is computed only once, and it transfers to problems with an arbitrary number of computers without any additional computation. So, our contribution in this paper is to learn a generalizable relational Q function that can express such a generalized policy and do it in a data-efficient manner. And to do so, we use abstraction in conjunction with deep learning and leapfrogging to learn a generalizable relational Q function. One key challenge in transfer is that problems with different object names and quantities have completely different Q tables since their state spaces are different. So to express a generalized policy, we need a way to lift problem-specific characteristics like object names and quantities, and we must be able to do so in a way that is tractable while maintaining the expressiveness. We use state and action abstraction to lift such problem-specific information by defining a feature list which consists of a set of features where each feature is an arbitrary first-order logic formula. We then define a feature kernel for the feature, which is a function that maps a state S to a set of objects. Our feature list is composed of description logic-based features from prior work of Bonnet and Francis. As an example, let f equal to running be a feature, where the feature kernel then evaluates the set of computers that are running. For the sysadmin 6 example, only computer C5 is not running, so the feature kernel evaluates to all other computers except C5. It can be easily seen that once the set cardinality of this feature kernel is taken, problem-specific object names and numbers are lifted away, and only numeric values regarding the abstract state are there. So we exploit this into doing deep learning for transfer, where we use the feature list to compute abstract state and action vectors, and then we can use fixed size MLP layers to allow transfer between instances. And this allows learning a generalized Q function that can zero-shot knowledge transfer between different problem instances. Our overall algorithm is as follows. We initialize a random policy for a problem that needs to be solved, in this case sysadmin 2, and the next step is to transfer the policy using GRL. In this case, the highlighted cells indicate the optimal action. For example, when no computers are running, you can reboot in any of the computers. Generalization might not be perfect, so the next step we can do instance-specific Q-learning on the policy to learn an instance-specific optimal policy, and this is guaranteed to be converged. And as we are doing this, we can always improve the generalized policy by iteratively improving the generalization capabilities by transitions encountered during the instance-specific learning. And this lends itself to scaling up Q-learning by using leapfrogging, by using a problem generator to learn the generalized policy from small examples. In our empirical evaluation, we use 4 tasks from the IPPC and a baseline is MBRRL, which transfers knowledge using conjunctive first-order features. We also compare with a GNN-based approach, which is not directly applicable because it uses closed-form action models. Our training setup, where we use the same training problems as published for the authors for the baselines and use leapfrogging for GRL. And in our test setup, we have test problems which are much larger than the training problems in terms of the state space size. Now I'll showcase our results. The x-axis is the IPPC problem instance number, and the y-axis is the average reward, and taller bars are better. It can be seen for sysadmin that GRL outperforms the baseline MBRRL in zero-shot transfer performance, and this trend carries over to the other domains as well. GRL is also competitive with SymNet, even though GRL does not receive closed-form action models like SymNet. In conclusion, we introduce a new approach that uses relational abstractions for generalized RL, and our experimental results show that our approach can outperform existing work. Please do stop by the poster session for a detailed discussion. Thank you.